Picture this: a vast, endless expanse where stars flicker like distant campfires, galaxies swirl in silent dances, and black holes lurk in the shadows, swallowing light itself. Out there, beyond the reach of our telescopes and probes, lies a universe teeming with questions that defy answers. What if everything we think we know about the cosmos is just the tip of the iceberg? What if the universe is hiding secrets so profound they could rewrite the very laws of physics? For centuries, humanity has gazed at the night sky, searching for meaning in the patterns of the stars. Yet, the more we discover, the more the cosmos seems to unravel before us, revealing puzzles that leave even the brightest minds stunned. From the eerie silence of the Fermi Paradox to the ghostly whispers of dark matter, the universe is a labyrinth of mysteries waiting to be explored. And today, we're embarking on a journey through 25 of the most baffling, mind-bending enigmas, questions that challenge our understanding of reality itself. This isn't just a list of cosmic curiosities, it's an invitation to step into the unknown. Some of these mysteries might keep scientists awake at night, while others could hold the key to our very existence. Are we truly alone, or is something or someone out there watching? Why does 95% of the universe remain invisible to us, and what lurks in the voids between galaxies where the rules of physics seem to bend? Strap in, because by the end of this journey, you'll see the cosmos not as a static backdrop, but as a living, breathing riddle, one we're only beginning to decipher. One summer night in 1977, an astronomer working with Ohio State University's Big Ear radio telescope made a discovery that would haunt scientists for decades. For 72 seconds, a burst of radio waves 30 times stronger than the background noise of space screamed across the cosmos, hitting Earth with a signal so precise it seemed almost artificial. When the researcher, Jerry Amon, circled the data on the printout in red ink, he scribbled one word in the margin: "Wow." That single word gave the signal its name, and to this day, it remains one of the most tantalizing, unsolved mysteries in astronomy. The wow signal came from the direction of the constellation Sagittarius, a region relatively empty of stars or known celestial phenomena. It matched the exact frequency scientists predicted an extraterrestrial civilization might use, one that hydrogen emits naturally, a kind of cosmic hello, if advanced beings were trying to communicate. But here's the strangest part: the signal never repeated. Despite decades of searching, no telescope has ever picked up anything like it again. Was it a brief, accidental blip from a passing comet, a glitch in the equipment, or something far more extraordinary, a fleeting message from another world sent across the void only to vanish before we could reply? Theories range from the mundane to the mind-bending. Some argue it could have been a reflected signal from human-made space debris bouncing back in an unexpected way. Others suggest a natural astrophysical event, like a yet unknown stellar phenomenon. But the most spine-tingling possibility is the one that lingers in the imagination: an alien transmission, a one-time beacon from a civilization that flickered briefly into our awareness before disappearing forever. With no way to verify its source, the wow signal stands as a cosmic Rorschach test. What we see in it may say more about us than the universe. And until another like it appears, this 72-second enigma will keep us staring at the stars, wondering who or what might be out there listening. Take everything you can see in the night sky, the stars, the galaxies, the swirling nebulae, and multiply it by 20. That's how much of the universe we're actually missing. Because here's the unsettling truth: roughly 85% of all matter in existence is completely invisible to us. It doesn't glow, reflect, or absorb light. It doesn't interact with the electromagnetic forces that make the cosmos visible. And yet, without it, galaxies would fly apart, the universe's structure would collapse, and our very existence would be impossible. This phantom scaffolding of the cosmos has a name: dark matter. The story of dark matter begins with a cosmic detective story. In the 1930s, astronomer Fritz Zwicky noticed something bizarre about the Coma Cluster, a massive group of galaxies. Based on the visible matter he could observe, the galaxies were moving far too quickly, so fast that gravity alone shouldn't have been able to hold the cluster together. There had to be something else, something invisible, exerting an irresistible gravitational pull. Decades later, scientist Vera Rubin found the same phenomenon in spiral galaxies, where stars at the edges were orbiting just as fast as those near the center, defying Newton's laws. The only explanation, an enormous halo of unseen matter, bending spacetime like an unseen hand guiding the cosmos. So what is dark matter? The leading theory suggests it's made of exotic particles that rarely interact with normal matter. Think of them as cosmic ghosts passing through you right now without a trace. Experiments like the Large Hadron Collider are smashing particles together, hoping to create these elusive entities in the lab. Meanwhile, detectors buried deep underground wait for the faintest shudder of a dark matter particle colliding with ordinary atoms. Yet after decades of searching, we've found nothing conclusive. Some scientists speculate dark matter could be primordial black holes, leftovers from the Big Bang. Others propose entire dark sectors of particles with their own hidden forces. The stakes couldn't be higher. Dark matter isn't just a cosmic curiosity. It's the glue holding galaxies together, the blueprint for the universe's large-scale structure. Without it, the night sky would be empty, and if we ever do uncover its secrets, it could rewrite the rules of physics, revealing dimensions or forces we never dreamed existed. Until then, dark matter remains the universe's ultimate vanishing act, everywhere and nowhere, shaping reality while staying forever just out of sight. If dark matter is the universe's invisible scaffolding, then dark energy is its mysterious engine pushing the cosmos apart faster and faster against all expectations. Picture a balloon inflating at an ever-increasing speed, not because someone's blowing into it, but because the rubber itself is stretching on its own. That's the eerie reality astronomers stumbled upon in the late 1990s when they measured distant supernova and made a jaw-dropping discovery. The expansion of the universe isn't slowing down due to gravity, as everyone assumed. It's accelerating, and whatever's causing this cosmic runaway, we have no idea what it is. The implications are staggering. Dark energy, the placeholder name for whatever's driving this acceleration, makes up an estimated 68% of the universe's total energy. Unlike dark matter, which pulls galaxies together, dark energy does the opposite, stretching spacetime itself. Think of it as anti-gravity, a repulsive force woven into the fabric of reality. Einstein actually predicted something similar with his cosmological constant, a fudge factor he later called his greatest blunder. But now it seems he might have been onto something after all. What makes dark energy so baffling is how it defies every conventional explanation. Some theories suggest it's a property of empty space itself, vacuum energy that grows stronger as the universe expands. Others propose it's a never-before-seen force field, dubbed quintessence, that changes over time. But here's the problem. When physicists calculate how much energy empty space should have based on quantum mechanics, the numbers are off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the worst mismatch in scientific history. The fate of the cosmos hangs in the balance. If dark energy continues unchecked, it could lead to a big rip where galaxies, stars, and even atoms are torn apart in a catastrophic finale. Alternatively, it might fade away, allowing gravity to regain control. Or perhaps it's just the first hint of a deeper layer of physics we've yet to uncover. Right now, telescopes like Euclid and the Vera Rubin Observatory are mapping the universe's expansion in unprecedented detail, hunting for clues. But until we crack this enigma, one thing's certain: the universe isn't just expanding, it's running away from us, and we're left chasing shadows in the dark. Imagine a galaxy teeming with billions of stars, each potentially hosting planets ripe for life. The numbers alone suggest we shouldn't be alone. With hundreds of billions of galaxies in the observable universe, the probability of other civilizations seems almost guaranteed. And yet, when we scan the cosmos for signs of intelligence, radio signals, megastructures, even alien probes, we're met with silence. This glaring contradiction is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" One unsettling explanation is the Great Filter, a hypothetical barrier so extreme it prevents life from advancing to interstellar communication. The terrifying possibility, the filter might still lie ahead of us. Think of it as a cosmic gauntlet. Perhaps the leap from single-celled organisms to complex life is extraordinarily rare, or maybe every advanced civilization inevitably destroys itself through war, climate collapse, or rogue AI. If that's true, humanity's silence could be a grim warning, a sign that no species survives its own technological adolescence. Others propose less apocalyptic answers. The zoo hypothesis suggests Earth is deliberately left untouched, like a nature preserve, observed but not disturbed. Another theory argues that advanced civilizations might abandon radio waves, using technologies we can't yet detect, neutrino communication or quantum entanglement. Or perhaps we're simply too early to the party, emerging in a universe still young, where intelligent life is just beginning to stir. Then there's the dark forest theory, inspired by survival instincts. Imagine the cosmos as a vast, dangerous woodland where every civilization hides, fearing that any signal, any reveal of their existence might attract predators. In this scenario, silence isn't just absence, it's strategy. The Fermi Paradox forces us to confront profound questions about our place in the universe. Are we alone because life is miraculously rare, or because something terrible awaits all who reach our stage? Is the silence a quarantine, a phase, or a trap? Until we find proof or another civilization finds us, this paradox remains a haunting reminder of how little we truly understand. In the vast silence of space, there are screams, brief, intense, and utterly mysterious. They last just milliseconds, but in that flash, they release as much energy as the sun does in decades. These are fast radio bursts, or FRBs, some of the most enigmatic signals ever detected. First discovered in 2007, they arrive without warning from galaxies billions of light-years away, vanish almost instantly, and leave astronomers scrambling for answers. What makes FRBs so baffling is their sheer power paired with their randomness. Imagine a cosmic strobe light flashing once, unpredictably, from the depths of the universe. Some burst once and never repeat, while others, like FRB 1211, fire off sporadically, teasing scientists with fragments of a pattern. The leading theory points to magnetars, highly magnetic neutron stars that could unleash these bursts when their crusts crack under immense stress, sending shockwaves through their magnetic fields. In 2020, astronomers caught a magnetar in our own galaxy emitting an FRB-like signal, adding weight to the idea. But not all bursts fit this explanation. Some are far too energetic or repeat too regularly, leaving room for wilder possibilities. Could some FRBs be evidence of advanced alien technology? The hypothesis isn't as far-fetched as it sounds. A sufficiently advanced civilization might use focused radio beams similar to a lighthouse to propel light sails across interstellar distances. The bursts could be accidental leakage from these powerful transmitters. While there's no proof, the sheer intensity and brevity of FRBs keep this speculative door slightly ajar. Studying them is like trying to capture lightning in a bottle. By the time telescopes swing toward the source, the burst is already fading. New instruments like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, are revolutionizing the hunt, detecting dozens of FRBs monthly. Each one is a cosmic breadcrumb, potentially leading us to uncharted physics or something even more extraordinary. Somewhere in the depths of space, an invisible force is pulling us toward the unknown. 500 million light-years away, hidden behind the thick dust and stars of our own galaxy's plane, lies a gravitational monster so powerful it's dragging entire galaxies, including our Milky Way, toward it at over 2 million kilometers per hour. Astronomers call it the Great Attractor, and it remains one of the most perplexing cosmic mysteries simply because we can't see it. The story begins in the 1970s, when scientists mapping the universe's large-scale structure noticed something bizarre. Thousands of galaxies, including ours, were all streaming toward the same patch of sky near the constellations Centaurus and Hydra. The motion defied expectations. The expansion of the universe should send galaxies drifting apart, not clustering toward a single point. Calculations revealed this mysterious region had the mass of tens of thousands of Milky Ways, concentrated in a space just a few 100 million light-years across. But when astronomers pointed their telescopes in that direction, they hit a wall. Literally, the Great Attractor sits directly behind what's called the zone of avoidance, an area obscured by the dense gas, dust, and stars of our galaxy's disk. Think of it as trying to peer through a blizzard. Visible light gets swallowed, leaving only faint radio and infrared glimmers to hint at what lies beyond. Early observations suggested a massive cluster of galaxies, dubbed the Norma cluster, might be the culprit, but later studies revealed even this colossal structure wasn't nearly heavy enough to explain the staggering pull. So what's really out there? One startling possibility is that the Great Attractor isn't the final destination, it's just a waypoint. Beyond it lies an even more enormous structure, the Shapley supercluster, a megacluster of galaxies so vast its gravity might be tugging everything toward it, including the Great Attractor itself. This cosmic tug-of-war reveals a universe far more interconnected than we ever imagined, with invisible threads of gravity weaving galaxies into a web we're only beginning to map. Efforts to pierce the zone of avoidance are yielding slow, tantalizing progress. Satellites like the X-ray observatory Suzaku have detected hints of hidden galaxy clusters, while infrared telescopes peer through the dust to reveal dim, distant stars. Each new glimpse adds another piece to the puzzle, but the Great Attractor keeps its secrets close. Whether it's a dense knot of dark matter, a supercluster we've yet to fully chart, or something even stranger, one thing is clear. The universe is pulling us toward a mystery, and we're just beginning to understand the force behind the tug. Out in the constellation Cygnus, roughly 1,400 light-years from Earth, a star behaves unlike any other we've ever seen. KIC 8462852, nicknamed Tabby star after astronomer Tabetha Boyajian, who first flagged its strangeness, flickers and dims in ways that defy every known rule of stellar physics. Imagine sitting by a campfire that suddenly, unpredictably, plunges into near darkness not once but repeatedly with no apparent rhythm or reason. That's the baffling reality astronomers face when observing this celestial oddity. The mystery began in 2015 when data from NASA's Kepler Space Telescope revealed jaw-dropping dips in Tabby's star's brightness, some as steep as 22%. Stars can dim slightly if planets pass in front of them, but even a Jupiter-sized world would block barely 1% of the light. These drops were massive, irregular, and sometimes lasted for days. Even stranger, historical records showed the star's overall brightness had faded by a staggering 14% over the past century, something stars of its type simply don't do. Initial theories ranged from mundane to mind-blowing. Could a swarm of comets pulverized into dust be orbiting the star in a bizarre, clumpy formation? Perhaps a colossal collision between planets left behind a debris field so thick it periodically eclipses the star. But when astronomers looked for the infrared glow such dust should emit, they found nothing. That's when the wildest hypothesis emerged: alien megastructures, specifically a Dyson swarm, a hypothetical network of energy collecting satellites or panels built by an advanced civilization to harness their star's power. The idea, first proposed by physicist Freeman Dyson, might explain the erratic dimming if such structures were partially completed or unevenly distributed. Yet the megastructure theory, while tantalizing, remains a last resort. Occam's razor suggests nature is more likely the culprit than extraterrestrial engineering. More recent studies point to fine, unevenly distributed dust clouds, perhaps from disintegrating moons or a still-forming planet, as the probable cause. But even this explanation leaves gaps. Why does the dust not glow in infrared as expected? Why do the dimming events vary so dramatically in timing and depth? Tabby's star has become a litmus test for how we approach cosmic anomalies. It challenges astronomers to think beyond textbook scenarios, to entertain both the improbable and the revolutionary. Every new observation, whether from ground-based telescopes or space observatories, adds another piece to the puzzle, yet the full picture remains frustratingly out of reach. For now, this enigmatic star keeps its secrets, a cosmic wink reminding us that the universe still holds wonders we can't yet explain. In the silent void beyond Pluto, two robotic explorers, Pioneer 10 and Pioneer 11, drifted toward the stars, carrying humanity's first messages to the cosmos. These hardy probes, launched in the early 1970s, had already revolutionized our understanding of the solar system, snapping close-ups of Jupiter and Saturn. But as they ventured farther from Earth, something strange happened. Their speeds didn't match the predictions. An unseen force, subtle but persistent, was dragging them backward. Scientists first noticed the anomaly in the 1980s. The pioneers were slowing down more than they should have been, as if space itself had a whisper of friction. The deceleration was tiny, about a billionth of Earth's gravity, but over decades and billions of miles, the drift became undeniable. By the time NASA lost contact with Pioneer 11 in 1995, the probes had fallen hundreds of kilometers short of their expected positions. Dubbed the Pioneer Anomaly, this mismatch became one of spaceflight's greatest head-scratchers. At first, engineers suspected mundane explanations. Could heat radiating from the probe's plutonium power sources be acting like a gentle thruster, pushing them backward? Computer models suggested this might account for part of the effect, but not all of it. Others wondered if solar wind or interplanetary dust played a role, but the numbers never quite added up. Then came the wilder theories. Some physicists proposed modified gravity, a tweak to Einstein's equations that might explain the deceleration without dark matter. Others whispered about unknown quantum effects or even unseen dimensions tugging at the probes from beyond our perception. The mystery lingered for decades, fueling speculation. Then in 2012, a team painstakingly reconstructed the probe's designs, accounting for every bolt and wire. Their breakthrough, the heat explanation, was correct, but with a twist. Earlier models had underestimated how much warmth Pioneer's electronics radiated in specific directions, creating an asymmetric push. Once factored in, the anomaly largely vanished. Case closed, not quite. A sliver of the deceleration still defies full explanation, leaving a crack in the door for something stranger. The Pioneer Anomaly stands as a humbling lesson. Even in the era of precision spaceflight, the cosmos can still surprise us with phantom forces and unexplained nudges. It reminds us that sometimes the universe's quietest whispers hold the loudest questions. On October 19, 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted something unprecedented streaking through our solar system, a visitor from another star. Named Oumuamua, Hawaiian for scout or messenger from afar, this mysterious object was the first confirmed interstellar traveler ever detected, and its bizarre behavior sparked debates that still rage today. What made Oumuamua so extraordinary wasn't just its origin, it was the way it defied classification. Unlike typical comets or asteroids, Oumuamua had a shape unlike anything in our solar system, long and thin, estimated to be up to 10 times as long as it was wide, tumbling through space like a cosmic cigar. Even stranger was its motion. As it hurtled away from the sun, it accelerated slightly, as if pushed by an unseen force. Comets often speed up due to outgassing ice turning to vapor, but Oumuamua showed no visible tail, no coma of gas and dust, nothing to explain the extra kick. Scientists scrambled for explanations. Could it be a fragment of a shattered planet ejected from another star system? A rare hydrogen iceberg, slowly evaporating in sunlight, leaving no trace. Some argued it might be a cosmic dust bunny, a porous aggregate of interstellar material unlike anything we've seen before. But the most provocative theory came from Harvard astronomer Avi Loeb, who suggested Oumuamua might be artificial, a solar sail or probe from an alien civilization using sunlight for propulsion. The idea wasn't entirely far-fetched. Humanity has already launched lightweight solar sails like Japan's Ikaro's mission. Critics countered that natural explanations were more likely. Later studies suggested Oumuamua's acceleration could be explained by the release of trapped hydrogen gas, a phenomenon never before observed but theoretically possible. Others proposed it was a shard of a Pluto-like world, rich in nitrogen ice that sublimated invisibly. The problem, we'll never know for sure. Oumuamua moved too fast, was detected too late, and is now beyond the reach of our telescopes, leaving only speculation in its wake. The legacy of Oumuamua isn't just about one odd object, it's about how unprepared we were to study it. Future telescopes, like the Vera Rubin Observatory, aim to catch interstellar visitors earlier, giving us time to probe their secrets. Until then, Oumuamua remains a tantalizing enigma, a cosmic postcard we barely had time to read before it vanished into the dark. Was it a comet, an asteroid, or something even more extraordinary? The universe, as always, keeps its secrets close. Deep in the heart of a black hole, where gravity warps reality into a singularity, lies a paradox so profound it threatens to unravel our understanding of physics itself. The problem, information, the fundamental code of the universe, appears to vanish without a trace. According to quantum mechanics, information can never truly be destroyed. It might scramble beyond recognition, but it should always persist in some form. Yet black holes, with their infinite gravitational grip, seem to break this rule. Anything that crosses their event horizon is lost forever, or is it? This dilemma, known as the black hole information paradox, began with Stephen Hawking's groundbreaking work in the 1970s. He showed that black holes aren't completely black. They emit a faint glow of particles now called Hawking radiation. Over eons, this radiation causes black holes to slowly evaporate, leaving behind nothing. No trace of the stars, planets, or atoms they consumed. The information about what fell in would seemingly be erased from the universe, violating quantum theory's sacred principle of reversibility. Imagine burning a book and watching its ashes vanish into thin air. Not just the pages, but every trace of the words themselves. That's the scale of the crisis physicists faced. For decades, the paradox fueled fiery debates. One radical solution proposed the existence of firewalls, lethal walls of energy, just inside the event horizon that incinerate anything falling in, preserving information at the boundary while turning the black hole's interior into a cosmic crime scene. But firewalls came with their own problems, contradicting Einstein's general relativity, which insists that crossing the event horizon should be uneventful, at least until spaghettification kicks in. Then came the holographic principle, a mind-bending idea that the information isn't lost at all, it's encoded on the black hole's surface like a cosmic QR code, projected into the interior like a three-dimensional hologram. Recent breakthroughs in string theory and quantum entanglement suggest that Hawking radiation might actually carry scrambled remnants of the original information, like echoes of a scream frozen in time. The puzzle isn't fully solved, but each twist in the story reveals how much we still have to learn. Black holes aren't just celestial vacuum cleaners, they're cosmic laboratories, testing the limits of reality itself. And as we peer deeper into their mysteries, we might not just crack the information paradox, we could uncover the hidden language of the universe. One of the most unsettling discoveries in modern cosmology isn't some distant anomaly. It's a pattern stamped across the entire sky, one that seems to know where we are. Scientists call it the axis of evil, a name that sounds like it's straight out of a cosmic horror story, and for good reason. When researchers mapped the cosmic microwave background, the faint afterglow of the Big Bang, they expected randomness, a uniform scatter of hot and cold spots left over from the universe's fiery birth. Instead, they found something that sent chills down their spines. The fluctuations weren't random at all. They were aligned eerily with the plane of our solar system. It's as if the universe left a fingerprint, and that fingerprint is pointing directly at us. The odds of this happening by chance, about 1 in 10,000. For context, that's like flipping a coin and getting heads 50 times in a row. At first, astronomers dismissed it as a fluke, a quirk of the data. But with each new satellite from WMAP to Planck, the alignment stubbornly persisted. The cosmic microwave background, our most pristine snapshot of the early universe, appears to have a preferred direction, and it's eerily linked to our own tiny corner of space. This isn't just a statistical oddity, it's a potential crisis for cosmology. The foundation of modern physics rests on the cosmological principle, the idea that on large scales the universe is the same everywhere with no special place or direction. Yet here we are, staring at evidence that we might, in some bizarre way, be special after all. Could there be a fundamental flaw in our understanding of the Big Bang? Some theorists suggest the alignment might hint at pre-Big Bang physics, relics of an earlier epoch that imprinted on spacetime itself. Others propose more radical ideas, that our universe is a hologram, or that it's collided with another universe, leaving a scar in the cosmic microwave background. Then there's the unsettling possibility that it's not the universe that's weird, it's us. Could some unseen bias in our measurements, some overlooked effect from our solar system's motion, be tricking us into seeing a pattern where none exists? Critics argue that foreground dust or galactic magnetic fields might be contaminating the signal, but try as they might, no one's been able to fully explain it away. The axis of evil lingers like a cosmic riddle, quiet but insistent. If it's real, it could rewrite our understanding of the universe's birth. If it's an illusion, it's one that's fooled our best instruments for decades. Either way, it's a reminder that the cosmos still has the power to unsettle us, to hint that, just maybe, we're not seeing the full picture. And until we crack this mystery, that eerie alignment will keep staring back at us, whispering that something fundamental is missing from the story we tell about reality. The moon today is a silent, airless world, its surface scarred by craters and dusted with regolith. But billions of years ago, it may have harbored a secret, a churning, molten heart that generated a magnetic field much like Earth. Rock samples brought back by the Apollo missions tell a tantalizing story. Tiny fragments of lunar basalt contain traces of magnetization, as if frozen in time from an era when the moon had its own protective magnetic shield. The puzzle: magnetic fields require a dynamo, a swirling, conductive core, and today's moon is geologically dead. So how did it vanish, and what does this mean for our celestial neighbor's violent past? For decades, scientists assumed the moon's core was too small and cold to ever power a dynamo. But in the early 2000s, reanalysis of Apollo-era data flipped the script. Measurements revealed that the magnetic imprints in lunar rocks were too strong to be explained by temporary fields, like those generated by asteroid impacts. Instead, they pointed to a global magnetic field, one that lasted for over 1 billion years. The leading theory suggests the moon's core was once hot enough to churn, fueled by two possible engines: either the slow crystallization of its molten mantle, releasing heat as it solidified, or something called precession, a wobble in the moon's spin caused by Earth's gravity, stirring the core like a spoon in coffee. But then, roughly 1 billion years ago, the magnetic field flickered out, the most likely culprit cooling. As the moon's interior lost heat, its iron core solidified, shutting down the dynamo. Yet this explanation isn't perfect. Some rocks suggest the field persisted longer than thermal models predict, hinting at another mechanism at play. One provocative idea involves massive impacts, like the one that carved the South Pole Aitken Basin, sending shockwaves through the moon's interior, jump-starting the dynamo one last time before it faded into silence. The implications reach far beyond lunar geology. If the moon had a magnetic field, it might have briefly sheltered a tenuous atmosphere, shielding volatile molecules like water ice from the solar wind's relentless stripping. That could explain why we find water trapped in shadowed polar craters today, frozen relics of a more dynamic past. It also challenges our assumptions about how small, rocky worlds evolve. Mercury, for instance, still has a weak magnetic field despite being only slightly larger than the Moon. Could other moons or exoplanets hide similar surprises? For now, the Moon's magnetic mystery remains half-solved, a ghostly echo of a time when our nearest celestial neighbor was more than just a silent sentinel. Future missions like NASA Artemis program aim to drill deeper, both literally and figuratively, into the lunar crust to uncover more clues. Until then, those magnetized rocks serve as tiny time capsules, whispering secrets about a moon that was once alive with hidden fire. In the constellation Bootes, about 700 million light-years from Earth, lies a cosmic nothingness so vast it defies comprehension. The Bootes Void, sometimes called the Great Void, spans an area of space roughly 330 million light-years across a spherical chasm so empty that if our Milky Way sat at its center, we wouldn't have seen another galaxy until the 1960s. This isn't just a quiet corner of the universe, it's a staggering desert, a place where galaxies should teem but instead barely whisper. When astronomer Robert Kirshner first stumbled upon the void in 1981, the discovery sent shockwaves through the astrophysics community. Standard models of galaxy formation suggested matter should clump together like foam in an ocean, leaving no room for such a colossal emptiness. The Milky Way, for context, resides in a filament of the cosmic web surrounded by thousands of neighboring galaxies. But the Bootes Void is home to just 60 or so, a number so low it's like finding a single grain of sand in an Olympic-sized swimming pool. Theories about its origin range from the mundane to the mind-bending. Some suggest it's the remnant of an ancient cosmic collision, where smaller voids merged like soap bubbles, pushing galaxies outward. Others propose it's evidence of a phenomenon called cosmic inflation, where rapid expansion in the early universe left behind patches of startling emptiness. But the most tantalizing and unsettling idea is that the void isn't empty at all. Instead, it might be filled with dark energy, the same mysterious force accelerating the universe's expansion, acting as a repulsive gravity that cleared the space of galaxies over eons. Yet even these explanations strain to account for the void's sheer scale. Simulations of the universe struggle to produce voids this large, leading some to wonder if the Bootes Void is a statistical fluke, a 1 in a billion accident, or if our models of structure formation are missing a crucial piece of physics. Could there be forces at work we haven't yet imagined, sculpting the cosmos in ways we don't understand? The void's eerie silence offers more than just scientific intrigue. It serves as a humbling reminder. For all our maps of the cosmic web, for all our theories about dark matter and dark energy, the universe still holds pockets of profound mystery. The Bootes Void doesn't just challenge our models, it dares us to look deeper, to consider that the fabric of reality might be stranger and more subtly woven than we ever suspected. Think of the universe's ledger, the grand accounting of all matter and energy that should exist based on our best models of the Big Bang. Dark matter and dark energy make up the vast majority, but even the normal matter, the stuff we're made of, the stars, planets, and galaxies we can see, has a glaring discrepancy. About half of it is missing, not hidden as exotic particles or mysterious forces, but ordinary protons and neutrons that should be out there somewhere. This is the missing baryon problem, and it's one of cosmology's most stubborn headaches. Baryons are the building blocks of visible matter, protons and neutrons that form atoms, which in turn make up everything from your body to distant quasars. Based on the cosmic microwave background and the universe's initial recipes, scientists calculated exactly how much baryonic matter should exist today. Yet when they tallied up all the stars, galaxies, and gas clouds they could observe, the numbers fell shockingly short. Nearly 50% of the expected baryons were unaccounted for, as if the universe had misplaced an entire mountain of atoms. So where could they be? The leading suspects aren't black holes or rogue planets, but vast, diffuse filaments of million-degree gas strewn between galaxies. Picture the universe's large-scale structure as a cosmic web, threads of dark matter weaving through space, with ordinary matter clinging to them like dew on a spider's silk. These filaments, too faint to emit visible light, glow faintly in X-rays, hinting at reservoirs of hot, ionized gas. But detecting them is like trying to spot a candle in a fog bank from miles away. Enter tools like the European Space Agency's XMM Newton telescope and NASA Chandra X-ray Observatory, which have begun teasing out traces of this hidden matter. In 2017, astronomers finally caught a breakthrough. By studying the distortion of X-rays from distant quasars as they passed through these filaments, they confirmed patches of the missing baryons. The gas wasn't just hot, it was searing, stretched so thin it had evaded detection for decades. Yet even this discovery only accounts for a fraction of the deficit. Some theorists suggest more baryons might lurk in even sparser regions, or perhaps as ultra-fast particles ejected by supernova. Others speculate that our understanding of the early universe's baryon count might need tweaking, a humbling reminder that cosmic bookkeeping is far from settled. The hunt for these missing baryons is more than academic. They're the hidden threads stitching the cosmic web together, shaping how galaxies form and evolve. Finding them isn't just about solving a puzzle, it's about completing the map of our universe's most fundamental architecture. And until every last atom is accounted for, the cosmos keeps a secret right under our noses, or rather, in the spaces between everything we see. At Saturn's North Pole, a storm rages unlike anything else in the solar system, a perfect, rotating hexagon large enough to swallow 4 Earths whole. First spotted by Voyager probes in the 1980s, this 6-sided behemoth has puzzled scientists for decades. Clouds whip around its edges at over 300 miles per hour, yet the shape remains eerily stable, its geometric precision defying everything we know about fluid dynamics and atmospheric chaos. What makes the hexagon so baffling is its persistence. Earth's hurricanes dissipate in days or weeks, while Jupiter's great red spot, though centuries old, shifts and shrinks over time. Saturn's hexagon, by contrast, has maintained its razor-sharp edges for at least 40 years, possibly much longer. The structure is so precise it looks almost artificial, as if etched into the atmosphere by some unseen cosmic hand. Laboratory experiments on Earth can create temporary polygonal shapes in spinning fluids, but nothing on this scale or duration. So how does a gaseous planet with no solid surface to anchor it sustain such perfect geometry? One leading theory points to deep-rooted jet streams. Saturn's atmosphere is layered like an onion, with winds shearing against each other at different altitudes. Computer simulations suggest that when these winds interact at specific speeds and depths, they can generate standing wave-stable patterns that rise through the turbulence like a vibrating guitar string. The hexagon may be one such wave, frozen in place by the interplay between Saturn's rapid rotation and the churning depths below. Another idea involves something called Rossby waves, large-scale atmospheric ripples that can trap energy in polygonal shapes, though none observed elsewhere match this level of symmetry. But the hexagon's mysteries don't end with its shape. Infrared imaging reveals a towering wall of clouds at its edges, some 60 miles high, where warm air from Saturn's depths collides with frigid upper layers. Even stranger, the hexagon changes color with Saturn's seasons, shifting from golden to blue as sunlight creeps back over the pole after years of darkness, hinting at chemical reactions we don't fully understand. Some researchers speculate the hexagon might be a window into Saturn's hidden interior. The planet's core, possibly rich in exotic states of hydrogen, could generate magnetic or gravitational anomalies that influence atmospheric currents. Others wonder if the hexagon is a cosmic coincidence, a rare resonance of forces that might vanish as suddenly as it appeared. For now, Cassini's final close-up images remain our best glimpse of this otherworldly storm. Future missions might unravel its secrets, but until then, Saturn's hexagon stands as a humbling reminder. Even in our own solar system, nature can sculpt wonders that defy every expectation. Just beyond Neptune's orbit, the solar system doesn't fade quietly into darkness. It ends with a cosmic cliffhanger. Astronomers call it the Kuiper Cliff, a mysterious boundary roughly 4.5 billion miles from the Sun, where the bustling population of icy objects in the Kuiper belt suddenly plummets to near zero. It's as if someone drew a line in the celestial sand and commanded everything beyond it to disappear. This abrupt edge defies expectations because, according to our models of solar system formation, the Kuiper belt should extend much farther, gradually thinning out like the fading ripples of a pond. So why does this frozen reservoir of comets and dwarf planets come to such an unnatural halt? One spine-tingling possibility is the gravitational hand of an unseen giant, Planet 9. This hypothetical world, estimated to be 5 to 10 times Earth's mass, could orbit hundreds of times farther out than Pluto. Computer simulations show that such a planet's gravity might shepherd Kuiper belt objects into clustered orbits while clearing out a stark boundary, like a cosmic sheepdog corralling its flock. The math is compelling. Several distant objects in the Kuiper belt already exhibit strange, aligned orbits that suggest an invisible perturber. Yet after years of searching, telescopes haven't spotted this phantom planet. Could it be hiding in the glare of the Milky Way, or is its absence telling us something even stranger about our solar system's history? Not everyone is convinced Planet 9 is the culprit. Alternative theories propose the cliff might be a fossilized relic of the Sun's birth environment. Our star formed in a crowded stellar nursery, where close encounters with sibling stars could have stripped away the outer Kuiper belt like a celestial thief in the night. Others suggest that Jupiter's migration early in the solar system's history scattered most outer material inward, leaving behind only a sparse population that coincidentally ends at the cliff's edge. Even more radical ideas involve rogue interstellar objects, perhaps a passing star or black hole, that gravitationally sculpted the belt billions of years ago. The Kuiper Cliff isn't just a curiosity, it's a potential Rosetta Stone for understanding planetary systems. Exoplanet surveys reveal that similar drop-offs exist around other stars, suggesting this phenomenon might be universal. Future telescopes like the Vera Rubin Observatory could finally spot Planet 9 if it exists, or uncover new clues about the violent processes that shape solar systems in their infancy. Until then, this silent boundary stands as a reminder. Even in our own cosmic backyard, the most basic questions about where space ends and emptiness begins remain unanswered. Among the countless nebulae drifting through our galaxy, one stands out as if it were crafted by an artist rather than nature. The Red Rectangle Nebula, nestled 2,300 light-years away in the constellation Monoceros, is a cosmic anomaly, a near-perfect geometric spectacle glowing with hues of deep crimson and eerie blue. Unlike the chaotic swirls of most nebulae, this structure boasts an almost symmetrical X shape, framed by ladder-like rungs of dust that give it the appearance of a celestial honeycomb. The strangest part, no one expected a dying star to create something so precise, so architectural. At the heart of this enigma lies a binary star system, two aging suns locked in a slow gravitational dance. One of them, a post-red giant star, is shedding its outer layers in violent bursts, while its companion star funnels this expelled material into two opposing cones. Think of it like a spinning garden sprinkler, except instead of water, it's blasting gas and dust into space at staggering speeds. Normally, such outflows would create a messy, spherical shell. But here, the binary star's orbital motion sculpts the ejector into that unmistakable X, with the rungs forming as shockwaves compress the dust into dense, evenly spaced rings. Then there's the color, a haunting red that seems too vivid for the depths of space. The hue comes from a rare form of carbon molecules called polycyclic aromatic hydrocarbons, or PAHs, which fluoresce under ultraviolet light from the dying star. These molecules, also found in soot and interstellar dust, are stacked in unusual formations here, amplifying the nebula's ruby glow. Meanwhile, the blue tints arise from scattered starlight bouncing off microscopic dust grains, creating an ethereal contrast that makes the red rectangle one of the most photogenic mysteries in the cosmos. Yet the more we study it, the more questions arise. Why are the dust rungs so evenly spaced? Some theorists suggest they're caused by periodic eruptions from the star, like cosmic tree rings marking its death throes. Others propose resonant vibrations, sound waves trapped in the outflowing material, could be shaping the structure. And then there's the unsettling possibility that we're witnessing a fleeting phase, a brief window where physics and geometry align just so, before the nebula dissolves into the interstellar void. What makes the red rectangle truly extraordinary is how it challenges our assumptions. Most dying stars create chaotic planetary nebulae, but this one defies the template, offering a glimpse into how binary systems can impose order on chaos. It's a reminder that the universe doesn't just build, it designs, crafting wonders that blur the line between accident and artistry. And as this cosmic rectangle continues to fade, its secrets remain locked in those crimson bands, a puzzle written in stardust and light. Imagine a galaxy spinning effortlessly, its stars orbiting gracefully without the invisible hand of dark matter guiding their motion. This isn't a thought experiment, it's real. Nestled in the constellation Cetus, 65 million light-years from Earth, lies NGC 1052DF2, an enigmatic galaxy that defies one of cosmology's most fundamental rules. Unlike every other known galaxy of its size, this cosmic oddity appears to have no dark matter at all. Its stars move precisely as Newton's laws predict, as if the universe forgot to include the shadowy scaffolding that holds galaxies together. Dark matter's absence here isn't just surprising, it's revolutionary. For decades, the case for dark matter rested on its gravitational fingerprints, the way galaxies rotate too fast to be held together by visible matter alone, how light bends around galaxy clusters, and the intricate cosmic web traced by billions of galaxies. Then along comes DF2, a ghostly, see-through galaxy with hardly any dense central region, no spiral arms, and most shockingly, no need for dark matter to explain its motions. When astronomers first measured its star's velocities in 2018, the numbers were perplexingly low. Without dark matter's extra gravity, the galaxy should have flown apart long ago. Yet there it floats, serene and seemingly untouched by the force shaping the rest of the cosmos. The discovery sent ripples through astrophysics, sparking fierce debates. Skeptics argued that DF2's distance might have been miscalculated, throwing off mass estimates. Others wondered if tidal forces from a neighboring galaxy had stripped away its dark matter like a thief in the night. But follow-up observations only deepened the mystery. Not only was DF2's distance confirmed, but another oddball, DF4, was found nearby, also bereft of dark matter. The implications are staggering. If dark matter can be separated from galaxies, does that mean it's a particle that can be tugged away rather than an intrinsic property of spacetime? Or does DF2 hint at something even more radical, that our understanding of gravity itself needs revising? Enter modified Newtonian dynamics, or MUND, an alternative theory suggesting gravity behaves differently at cosmic scales. MUND proponents argue DF2's star motions fit their models perfectly, making dark matter unnecessary. But critics fire back. If MUND were correct, all galaxies should behave like DF2, not just a rare few. Meanwhile, dark matter loyalists propose these galaxies might be failed systems, born in environments so sparse they never accumulated much dark matter to begin with. The most tantalizing clue lies in DF2's pristine, ancient stars. Their chemistry suggests the galaxy formed slowly, in isolation, avoiding the violent mergers that typically bundle dark matter with visible matter. If true, DF2 isn't an anomaly, it's a cosmic fossil preserving a rare, quieter path of galaxy formation. Upcoming telescopes like the James Webb Space Telescope could peer into more of these dark matter-deficient galaxies, testing whether they're flukes or keys to a larger puzzle. For now, DF2 stands as a cosmic paradox. It doesn't disprove dark matter, but it does challenge us to ask deeper questions. Is the universe more inventive than we imagined, crafting galaxies by different rules? Or have we stumbled upon the exception that proves the rule, revealing dark matter's nature by its very absence? Whatever the answer, this ghostly galaxy reminds us that the cosmos still has surprises up its sleeve, and sometimes what's missing speaks louder than what's there. In 2019, astronomers sifting through radio telescope data stumbled upon something utterly unexpected: rings so vast they could swallow entire galaxies. These oddities, now called odd radio circles or ORCS, appear only in radio wavelengths, invisible to optical, X-ray, or infrared telescopes. Each one spans hundreds of thousands of light years, dwarfing the Milky Way, yet their origins remain shrouded in mystery. Imagine dropping a pebble into a cosmic pond and watching ripples expand far larger than the splash itself, except no one knows what dropped the pebble. The first ORC spotted, dubbed ORC-1, emerged during a sky survey by Australia's ASCAP telescope. At first, researchers assumed it was an imaging glitch. But then more appeared, each a near-perfect circle, some with bright edges like smoke rings frozen in space. The strangest part, they're empty at the center. No visible galaxies, no black holes, no obvious energy sources to explain their colossal radio glow. One leading theory suggests shockwaves from a cataclysmic event, perhaps two supermassive black holes merging millions of years ago, releasing energy equivalent to billions of supernova in a spherical burst. These waves would expand outward, lighting up surrounding gas like a neon sign in the cosmic void. Yet not all ORCS fit this mold. Some appear around galaxies with active cores, where jets from supermassive black holes might punch through intergalactic gas, creating bubble-like structures we see edge on as rings. Others float in isolation, far from any known galactic neighborhoods. That's where wilder ideas creep in. Could ORCS be the fingerprints of wormholes, tunnels in spacetime predicted by Einstein's equations, whose mouths might emit detectable radiation? Or are they echoes of dark supernova, hypothetical explosions from stars made entirely of dark matter, leaving no optical trace? Then there's the timing. ORCS seem rare, only a handful confirmed so far, but they might be more common than we think. Radio telescopes have only recently gained the sensitivity to detect such faint, diffuse structures. Future surveys could reveal thousands, rewriting our understanding of galactic ecosystems. For now, they stand as cosmic doodles, cryptic signatures hinting at physics we've yet to unravel. Every new ORC discovered isn't just another ring, it's a question mark floating in the dark, reminding us how much of the universe's language we still can't read. Deep in the equations of particle physics, there's a ghost hiding in the math, a theoretical specter so strange it doesn't even behave like a particle at all. Meet the unparticle, a hypothetical substance predicted by physicist Howard Georgi in 2007, defying everything we know about matter and energy. Unlike protons, electrons, or even dark matter, unparticles wouldn't have a fixed mass or obey the tidy rules of quantum mechanics. Instead, they'd exist in a fuzzy, in-between state, more like a cloud of possibility than a solid piece of reality. Picture trying to catch smoke with your hands. What you grasp isn't a single thing, but something that slips through your fingers in uncountable ways. The unparticle theory emerged from a radical rethinking of scale invariance, a property where physical laws look the same no matter how you zoom in or out. Most particles have distinct masses that anchor them to specific energy scales, but unparticles, they'd scale freely, leaving no clear footprint in detectors. You couldn't pin them down to a single interaction or energy level. This makes them nearly invisible to conventional experiments, lurking just beyond the edges of our perception. Why does this matter? Unparticles could be the missing link in some of cosmology's biggest puzzles. Their ethereal nature might explain dark matter's stubborn refusal to interact with ordinary matter, not because it's weakly interacting, but because it's not quite a particle at all. Or they could account for anomalies in high-energy particle collisions, where unexpected energy patterns crop up without explanation. Some theorists even speculate unparticles might influence the universe's expansion, weaving subtly into the fabric of dark energy. The challenge is detection. Traditional particle accelerators like the Large Hadron Collider hunt for sharp spikes in energy, signatures of particles with definite masses. Unparticles, though, would smear their signals across a range of energies, like a whisper spread over a crowded room. New approaches are needed, delicate quantum interference experiments, or precise measurements of gravitational waves that might carry unparticle imprints. Skeptics argue the theory is too abstract, a mathematical curiosity without tangible proof. Yet history shows physics often advances by chasing ghosts, from the neutrino, once deemed undetectable, to the Higgs boson, theorized decades before its discovery. Unparticles might be the next great leap or a beautiful dead end. Either way, they remind us that the universe's deepest secrets might not look like anything we've seen before. The unparticle isn't just a new particle, it's a challenge to rethink what particles even are. And in that ambiguity lies the thrill of the unknown. The Hubble tension is a cosmic riddle tearing at the seams of modern cosmology, a disagreement so profound it could rewrite our understanding of the universe's fate. On one side, we have the Hubble Space Telescope's meticulous measurements of the cosmos's expansion rate, pegged at roughly 73 kilometers per second per megaparsec. On the other, the Planck satellite's observations of the cosmic microwave background suggest a slower rate, around 67. These aren't minor rounding errors, they're fundamentally incompatible values separated by a gulf wider than measurement uncertainty can explain. And with each passing year, as instruments grow sharper and data piles higher, the gap stubbornly refuses to close. The stakes couldn't be higher. The Hubble constant, the number that quantifies how fast the universe is stretching, isn't just a speed limit sign. It's a cornerstone of everything from the age of the cosmos to the nature of dark energy. If both measurements are correct, then something is deeply wrong with our models. The leading culprit, early dark energy, a hypothetical force that might have briefly surged during the universe's infancy, tweaking the primordial conditions Planck observes while leaving the Hubble telescope's nearby measurements unaffected. Think of it like a ghostly hand giving the infant universe an extra push, then vanishing without a trace. But skeptics argue the tension might stem from something far more mundane: human error. Could subtle calibration issues in Hubble's distance ladder, the chain of methods used to measure cosmic distances, be skewing the numbers? One controversial study suggested that quirks in the brightness of Cepheid variable stars, the universe's standard candles, might be throwing off calculations. Others propose that local peculiarities, like the Milky Way floating in an underdense cosmic bubble, are distorting our perspective. Yet the most electrifying possibility is that the Hubble tension is a signpost to new physics. What if dark energy isn't constant, as Einstein's cosmological constant assumes, but evolves over time? Or what if gravity itself behaves differently on cosmic scales, a notion championed by modified gravity theories? The answer might lie in next-generation tools like the James Webb Space Telescope, which could cross-check Hubble's measurements with unprecedented precision, or the upcoming Nancy Grace Roman Telescope, designed to map dark energy's influence across billions of years. For now, the Hubble tension remains an open wound in cosmology, a puzzle that refuses to be ignored. It's a reminder that the universe, for all our maps and equations, still holds cards close to its chest. Whether it's a flaw in our tools or a clue to something grander, one thing is clear: the cosmos is still teaching us how much we have left to learn. Somewhere in the cosmos, 5,000 light-years from Earth, spins a world so bizarre it defies imagination, a planet where rain isn't water but diamonds. PSR J1719-1438b, a mouthful of a name for a celestial oddity, orbits a pulsar so fast it completes an entire year in just 2 hours. But speed isn't its most astonishing feature. This planet, roughly the size of Jupiter, might be a colossal cosmic gem, its core crushed into crystallized carbon by unimaginable pressures. Picture an entire world glittering like a diamond under the starlight, its surface likely colder than ice, its heart compressed into something harder than any mineral on Earth. The story of this diamond planet begins with a stellar cataclysm. Its pulsar host, a rapidly spinning neutron star, was once part of a binary system, 2 stars dancing in tandem until one collapsed into a supernova, shredding its companion's outer layers. What remained was a stripped-down core, so dense its carbon-rich material was compressed into a crystalline lattice. Think of it like a pressure cooker on a cosmic scale. Under normal circumstances, carbon might form graphite or coal, but here, crushed by gravitational forces thousands of times stronger than Earth's, it's forged into something far more extraordinary. What makes this world even stranger is its origin story. Most pulsar planets shouldn't exist. Neutron stars are born in violent explosions that ought to obliterate any nearby worlds. Yet PSR J1719-1438b survived, likely because it wasn't always a planet. Astronomers speculate it might be the corpse of a white dwarf, a dead star's remnant that lost its outer layers to the pulsar's gravity, leaving behind a skeleton of crystallized carbon. If true, this diamond planet isn't just a curiosity, it's a cosmic phoenix, reborn from stellar ashes into something entirely new. The implications ripple far beyond one glittering oddity. Planets like this force us to rethink the boundaries of planetary science. We're used to rocky worlds like Earth or gas giants like Jupiter, but the universe is far more inventive. Carbon-rich planets could host mountain ranges of diamond, oceans of tar, or even skies thick with hydrocarbon smog. Some might argue that calling PSR J1719-1438b Diamond Planet is poetic license after all. Its interior is likely a mix of degenerate matter and exotic crystal states we can scarcely replicate in labs. But that's what makes it so fascinating. It's a laboratory for extreme physics, a place where matter behaves in ways that challenge our definitions. Could such a world ever be more than a cosmic trophy? Theoretically, its diamond-rich composition would make it a miner's dream, if mining a planet orbiting a lethal pulsar weren't suicidal. The pulsar itself bathes the planet in deadly radiation, and tidal forces likely keep one side perpetually locked in scorching heat while the other freezes in darkness. Yet even these extremes offer clues. By studying how planets survive or transform in such hostile environments, we learn about the resilience of matter itself. The diamond planet reminds us that the universe is a master alchemist turning stellar death into celestial jewels. It's not just a quirk of astronomy, it's a testament to the boundless creativity of cosmic forces. And as we discover more of these exotic worlds, we're forced to confront a humbling truth. The universe doesn't just make planets, it sculpts them into forms stranger than fiction. Most planetary systems behave like well-rehearsed orchestras, with planets orbiting neatly around a single star, all in the same flat plane. But in the constellation Orion, a cosmic rebel breaks every rule. GW Orionis, a triple star system located 1,300 light-years from Earth, hosts a planet on a path so wildly tilted it defies everything we know about how worlds form. Imagine a spinning top wobbling erratically around three suns. This is the bewildering dance happening in this stellar menagerie where gravity paints in chaotic brushstrokes. At the heart of the system, three young stars twirl in a complex gravitational ballet. Two orbit each other tightly while a third pirouettes farther out. Surrounding them is a colossal protoplanetary disk, a swirling ring of gas and dust where planets are born. But here's the twist, the disk isn't flat. It's warped like a crumpled vinyl record, split into distinct rings that tilt at jarring angles. Nestled within this cosmic labyrinth, a gas giant planet orbits at a steep incline, completely misaligned with the star's orbital plane. This isn't just unusual, it's a direct challenge to our models of planet formation, which assume orderly, flat disks give rise to orderly, flat systems. The mystery lies in the forces at play. In a single star system, a planet forms from material evenly distributed in a disk, its orbit naturally aligning with the star's spin. But add two more stars and chaos ensues. The competing gravitational tugs from GW Orionis's trio stretch and twist the disk, creating ripples and gaps. Some astronomers argue the star's gravitational torques alone could fracture the disk into misaligned rings. Others propose the planet itself might be the culprit, its gravity carving a tilted path as it plows through the dust. Then there's the startling possibility that this isn't a flaw in our theories, it's a revelation. GW Orionis might represent a different way planets can form, one where turbulence and gravitational warfare mold worlds into bizarre configurations. If true, tilted planets could be more common than we thought, especially in multi-star systems, which make up nearly half of all star systems in the galaxy. The implications ripple beyond this one system. If planets can form at extreme angles, it raises questions about the stability of their orbits and the potential for habitable conditions. A planet knocked askew might experience wild climate swings, its poles baked by sunlight one moment and plunged into icy darkness the next. Yet somehow, against the odds, GW Orionis's defiant planet persists, a testament to nature's ability to forge order from chaos. For now, telescopes like Oumuamua and the James Webb Space Telescope continue dissecting this cosmic oddity, peeling back layers of dust to uncover its secrets. What they find might not just solve the puzzle of GW Orionis, it could rewrite the playbook on how planets are born, reminding us that the universe favors creativity over conformity. Among the faint whispers of the cosmic microwave background, a cold spot lingers like a shadow in the aftermath of the Big Bang. This anomaly, spanning nearly 200 million light-years in the constellation Eridanus, is one of the universe's most perplexing relics. Temperatures in this region dip unexpectedly, far colder than standard models predict, as if a piece of the early cosmos refused to warm with the rest. Some scientists speculate this chill might be a bruise from a collision with another universe, a cosmic crash so violent it left an imprint on the fabric of our own. Others argue it's merely a vast, empty supervoid, a cosmic desert where the absence of galaxies creates a deceptive cold front. But neither explanation fits neatly, leaving room for something far stranger. The cold spot first caught astronomers' attention in 2004, when NASA Wilkinson Microwave Anisotropy Probe mapped the cosmic microwave background in unprecedented detail. This ancient light, released when the universe was just 380,000 years old, should be nearly uniform, with tiny fluctuations reflecting the seeds of future galaxies. Yet the cold spot stood out, a blistering contradiction to expectations. Follow-up observations only deepened the mystery. If a supervoid were responsible, it would need to be impossibly large, far exceeding the scale of any known structure. Void theory suggests that as light traverses these sparse regions, it loses energy, stretching into cooler wavelengths, an effect called the integrated Sachs-Wolfe effect. But even the most cavernous voids detected don't account for the cold spot severity. The numbers simply don't add up. That's where multiverse theories enter the picture. In some models of inflationary cosmology, our universe is one bubble among countless others in an eternal cosmic foam. If two bubbles brushed against each other in the early universe, the energy of that collision could have left a scar, a patch of space where the background radiation cooled anomalously. It's a radical idea, but not without precedent. The cold spot's texture aligns with predictions for such an encounter, resembling a kind of gravitational shadow cast by a neighboring universe. Supporters point to subtle irregularities in the spot's polarization patterns, hints that something beyond mere emptiness might be at work. Skeptics, however, aren't ready to rewrite physics just yet. They argue that statistical flukes exist in any dataset, and the cold spot might simply be a rare outlier in an otherwise predictable cosmos. Advanced simulations show that even in a universe without multiverses or exotic voids, anomalies of this scale can occasionally arise purely by chance. The real test will come with future surveys. Instruments like the Simons Observatory and the CMB S4 project aim to scan the cosmic microwave background with even finer precision, hunting for secondary signatures like distorted galaxy distributions around the cold spot that could tip the scales toward one theory over another. What makes this debate so electrifying isn't just the science, it's the philosophical stakes. If the cold spot is evidence of a parallel universe, it would be the first tangible clue that we're part of something vaster than our observable cosmos. On the other hand, if it's just a supervoid, it forces us to reckon with how little we understand about the large-scale structure of space. Either way, this frigid enigma reminds us that the universe's deepest mysteries often lurk in the quietest corners, waiting to reshape our understanding of reality itself. If black holes are the universe's ultimate one-way streets, swallowing everything that crosses their event horizons, then white holes could be their bizarre cosmic opposites, theoretical exits where matter and energy erupt outward in a burst of defiance against gravity's grip. Imagine a galactic fire hydrant blasting a jet of primordial material into space, or a cosmic rewind button that spits out stars instead of swallowing them. This isn't science fiction. It's a serious mathematical possibility lurking in Einstein's equations of general relativity, where time-reversed versions of black holes could exist as dazzling, impossible fountains of creation. The concept emerges from the same math that predicts black holes. While black holes form when massive stars collapse into singularities, points of infinite density, white holes would be their time-flipped counterparts, singularities that refuse anything from entering while violently expelling everything inside. Picture a black hole's event horizon as a door that only opens inward. A white hole's door would only open outward, hurling matter into the universe like a slingshot fired by spacetime itself. Some theorists suggest they could be the other end of black holes, connected via wormholes in a hypothetical tunnel through the fabric of reality. Others propose they might be remnants of a rebounding Big Bang, echoes of a universe that collapsed and then exploded anew, leaving behind these cosmic geysers. Yet for all their mathematical elegance, white holes face a glaring problem: thermodynamics. The second law states that entropy, or disorder, always increases in a closed system. A white hole defies this by seemingly creating order, spewing out pristine material in a way that looks suspiciously like entropy running backward. Some physicists argue this makes them impossible, or at least staggeringly unstable. Like a tower of blocks balanced perfectly on its tip, a white hole might collapse into a black hole at the slightest perturbation, vanishing before we could ever observe one. But what if they do exist, or did briefly? One tantalizing idea links them to gamma-ray bursts, the most energetic explosions in the universe. These fleeting, hyperluminous events could hypothetically be white holes blinking into existence for mere seconds before self-destructing. Even more radical is the notion that the Big Bang itself was a white hole erupting from a prior universe's black hole, a cosmic cycle of collapse and rebirth encoded in the geometry of spacetime. The search for evidence remains speculative. Unlike black holes, which betray their presence by bending light and accelerating stars, white holes would be far more elusive. Their outbursts might mimic other astrophysical phenomena, camouflaging themselves among supernova or quasars. Some researchers scan for anomalous bursts of particles with no apparent source, while others hunt for mathematical fingerprints in the cosmic microwave background, residual heat that might bear scars from these explosive events. White holes force us to confront the limits of our physical intuition. They challenge not just how we think about gravity, but how we think about time itself. Could the universe harbor regions where causality runs backward, where effects precede causes? Or are these glittering mathematical phantoms just mirages in the equations, beautiful ideas that reality simply refuses to permit? Whether they're hidden in plain sight or forever confined to theory, white holes remind us that the universe's strangest possibilities often lie just beyond the edge of what we can see. And sometimes the most profound mysteries aren't about what's out there, but what might be. From the haunting silence of the Fermi Paradox to the phantom tug of the Great Attractor, from the diamond rains of distant exoplanets to the warped geometry of Saturn's hexagon, these 25 cosmic mysteries aren't just puzzles waiting to be solved. They're humbling reminders of how much we don't know. For every question answered, the universe tosses us a dozen more, each more enigmatic than the last. Dark matter's invisible grip, the eerie alignment of the axis of evil, the fleeting whispers of fast radio bursts, they all point to a cosmos far stranger, far more inventive than our textbooks dare to describe. But here's the beauty of it: these aren't failures of science, they're invitations. Every unsolved riddle is a frontier, a challenge to rethink what we assume is possible. What if Oumuamua wasn't just a space rock, but a relic of another civilization? What if the cold spot in the cosmic microwave background is a bruise from a collision with another universe? The answers might rewrite physics, redefine reality, or even reveal our place in a grander tapestry we've only begun to glimpse. So let's keep asking. Let's stay restless, because curiosity didn't just build our understanding of the cosmos, it expanded it, stretching the boundaries of knowledge light year by light year. And who knows, the next great discovery might be hiding in data we've already collected, waiting for a fresh pair of eyes to connect the dots. Or maybe it's lurking in the shadows of a phenomenon we haven't even noticed yet. That's where you come in. The universe doesn't belong to just astronomers and physicists. It's ours to explore, debate, and marvel at together. So tell us in the comments, which of these cosmic enigmas keeps you up at night? Is it the ghostly pull of dark energy, the cryptic patterns of Tabby's star, or something we didn't even cover today? Share your thoughts, your wildest theories, and let's keep the conversation as boundless as the cosmos itself. After all, the next big revelation might start with a single question, and who's to say it won't be yours?